Hello everyone, welcome to MESS e-learning channel. So today we are going to do the last video in this series of videos in the topic nanoscience and nanotechnology. Prior to beginning with this video, let us have a quick recap of what we have done so far. So here are the various topics that we have covered so far. First, we had an introduction to nanoscience and nanotechnology. Next, we had the surface to volume ratio concept that is used in nanotechnology. The most important one, the two main approaches in nanotechnology, the top-down and the bottom-up approach. This was followed by the important tools in nanotechnology, basically the scanning electron microscope, and this was followed by another important tool, which is the transmission electron microscope, followed by the scanning probe microscopy tools, which comprised of the scanning tunneling microscope and the atomic force microscope. This was followed by various synthesis methods 1, 2 and 3 that comprised of ball milling, sputtering, sol gel, laser ablation, vapor deposition. And we have also done the applications of the nanomaterials part 1. Now we are going to do the applications of another important type of nanomaterial, and these are nothing but the carbon nanotubes. So the most common form of the carbon are graphite, diamond and amorphous carbon. Out of that, graphite and diamond is having a crystalline structure. Now, there are two allotropes of carbon nanomaterials. So, these allotropes of the carbon nanomaterials are fullerene and the carbon nanotubes. So, we will be focusing on carbon nanotubes, but let us see what are basically fullerenes, and let us also see what are basically carbon nanotubes. So, one of the allotrope of carbon nanomaterial is fullerene. This fullerene is basically a C60 molecule. That means it is having 60 atoms of carbon, and each of this atom is bonded trigonally to every other carbon atom. So here is basically the fullerene molecule. This fullerene molecule is having a football-like structure. So here is the basic structure of a football, for a comparison. And as you know that in a football structure, there are 20 hexagonal faces and there are 12 pentagonal faces. And in the same way, we are having the C60 molecule. The diameter of a C60 molecule is of the order of 7.10 angstroms. The second allotrope of carbon nanomaterials is basically the carbon nanotube. A carbon nanotube is basically a sheet of graphene, or other one can say a single sheet of graphite called as a graphene, which is rolled into itself. So such a kind of tube is called as a carbon nanotube, but there are some additions to this. On either side of this tube, there are half C60 molecules, and this entire assembly makes one carbon tube. So this is one entire molecule. The carbons inside this can be arranged in various ways, and the three different types of ways in which the arrangement can occur are the armchair type, the chiral type and the zigzag type. So based on these arrangements, you will actually have different types of carbon nanotubes. Carbon nanotubes are further divided into two types. Let us see these types. These are basically the single wall nanotubes and the multi-wall nanotubes. In short, SWNT and MWNT. The single wall nanotubes consist of a single sheet of graphite rolled on itself, and that's the reason why we call it as SWNT. Similarly, as the name suggests, MWNT or the multi-wall nanotube is actually comprised of multiple graphene sheets which are rolled on itself coaxially. So there may be somewhere around 50 nanosheets rolled into itself, and that is something that leads to the development of a multi-walled nanotube. Let us now study the properties of the carbon nanotubes. So here is the first property of the carbon nanotubes, and there is nothing but the tensile strain. And the tensile strength or the breaking strength of a carbon nanotube is 50 times that of steel. Not only that, but CNTs are extremely elastic. The following table shows a comparison of the properties of single wall nanotubes and multi-wall nanotubes as compared with that of steel. Now you have the value for the Young's modulus for single wall nanotube as 1054, for the multi-wall nanotube as 1200, and for the steel it is only 208. So you can see a comparison between this. There is almost an order of magnitude difference between single walled, multi-wall nanotube and that of steel. These values are measured. These are the values of the Young's modulus, and they are measured in gigapascals. Similarly, we are having the tensile strength values over here, and the value for the tensile strength for single wall nanotube is 150. That for multi-wall nanotube once again is 150, whereas that for steel, which is one of the hardest material that we know, the strongest material that we know, is only a 0.4. Nanotubes score a lot over the values of the Young's modulus and that of the tensile strength as compared with steel. The next property that we study for carbon nanotubes is that of thermal conductivity. All nanotubes, the carbon nanotubes, are expected to be very good thermal conductors along the tube, and they are actually good insulators laterally to the tube axis. Now the following table shows a comparison of the thermal conductivity values measured at room temperature as compared with that of copper. So we have the value for the multi-walled nanotube greater than 3000 watt per meter per Kelvin. That for the single wall nanotube is around 3500 watt per meter per Kelvin, whereas that for copper is as low as 385 watt per meter per Kelvin. Another important property that is applicable for the carbon nanotubes is their electrical conductivity. Now due to the symmetry and the unique electronic structure of graphene, the nanotubes will have a very high current carrying capacity, and due to that, that means they will have a very high conductivity, that is electrical conductivity. The following table shows the comparison of the values between the electrical conductivities for carbon nanotube and that for copper. So we have for the carbon nanotube, the value is somewhere around 10 raised to 6 to around 10 raised to 7, and that for copper the same value is of the order of 6 into 10 raised to 7 Siemens per meter. One more property that we have to consider for carbon nanotubes is basically their reactivity, the chemical reactivity. The chemical reactivity of a carbon nanotube is higher as compared with that of graphene, and that is due to the curvature of the CNT surface. Because due to the curvature of the CNT surface, we have a pi orbital mismatch, and this is how the reactivity, the chemical reactivity increases. So this means higher the curvature, or rather smaller the diameter, greater is going to be the chemical reactivity. So in a way, there is an inverse relationship between the chemical reactivity and the diameters of the carbon nanotubes. Having done with the properties of the carbon nanotubes, let us now focus on the applications of the carbon nanotubes. And one of the most important application of a carbon nanotubes is hydrogen storage. So hydrogen basically is a source of energy, and this can be easily generated, and also it is a non-pollutant. At the other end, the carbon nanotubes, now since they are hollow, Not only that, but this hollowness, the pore size is actually of the order of nanometers, and that is the reason why we can very well use this particular property of carbon nanotubes to effectively store hydrogen. Another application of carbon nanotubes is in the development of supercapacitors. So, what is a supercapacitor? As the word indicates, it will store a large amount of charge. The quantity of charge that is stored by it is quite large, and this can be used in several devices, in several electronic devices. Now, basically a capacitor comprises of two electrodes, and these two electrodes are separated by a dielectric electrochemical material. Now, the capacitance will depend upon the charge separation between the charge that is actually developed on the electrode and the counter charge that is developed in the dielectric electrochemical material. If you are using CNTs, then this separation is going to be of the order of nanometers, and therefore smaller the separation, larger is going to be the capacitance, because capacitance is inversely proportional to this separation, and thus a large amount of charge can be stored if at all we are using carbon nanotubes for the development of supercapacitors. One of the most important applications of a carbon nanotube is the formation of a field effect transistor. The field effect transistor is basically a 3-terminal device, and it is basically a switching device, and it is constructed from a single semiconducting single wall nanotube. So, here we will be using SWNTs. Now, in this case, whenever we apply a suitable voltage to the gate, then it will so happen that the nanotube will actually be switched from the conducting phase to the non-conducting phase. Such CNT, FET transistors are coupled to form a logic switch, which is the basic component of computers. We now move to the next application of carbon nanotubes, and there is nothing but the field emitting devices. We know that the electric lines are concentrated at sharp edges, that is the tips. We have this kind of sharp edges in carbon nanotubes, and this is actually favorable. Such a kind of situation is favorable for field emission of electrons using the concept of electron tunneling. Now, due to this material property, the field turn on voltage can be as low as 100 volts. Not only that, but these particular carbon nanotubes, due to this particular property of field emission of electrons, can be used for field emission displays. One of the last applications, last but not the least of course, is the nanoprobes and sensors made out of CNTs. Now, due to their flexibility, CNTs can actually be used in the scanning probe instruments. Specifically, since this MWNT, that is the multi-wall nanotubes, are highly conducting, they can be used in STM, that is the scanning tunneling microscope, as well as in AFM instruments, leading to improved resolution. Not only that, but due to the high gauge factor of a single walled carbon nanotubes, that is SWNTs, these can be used to sense the deformation of membranes due to the ambient pressure gradients, and thus they can actually be a very important component of a pressure sensing device. With this application, we have completed the video as well as the series of videos based on nanoscience and nanotechnology. Here is a quick recap of what we have completed so far, the list of the topics that we have completed in all the videos so far. I hope you have understood these videos. Thanks a lot.